Hello, this video will cover solving radical equations and inequalities. Example 1, the square root of x plus 4 is equal to 3. The first thing we need to do when we're solving any type of equation, we just need to work backwards. We need to use our inverse operations to solve for the unknown. So the first step is you isolate the radical on one side. The reason is so that you can get rid of the radical by squaring it, cubing it, whatever you might need to do. So here we go. It's already isolated, so we're done. So we're going to square. Because the index is 2, we will square. That's what undoes the square root. That's what the inverse is. So we square both sides, and we're left with x plus 4 is equal to 9. Then you repeat steps 1 and 2 if necessary. I'll talk about that. If you square something and it gets rid of one radical but you have another one, then you have to do steps 1 and 2 again. In this case we don't. We go for solving for x, so we subtract 4 and we get x equals 5. And then we check for what's called extraneous solution. So when I plug in x equals 5, the square root of 5 plus 4 is the square root of 9. Does that equal 3? And the answer is yes. So the solution x equals 5 is correct. Now, an extraneous solution are solutions that do not satisfy the original equation. Let me give you a quick example. Let's say I give you this equation x equals 2. And you decide that, just because of kind of what we're doing here, we want to square both sides. Well, if we square both sides, we get x squared is equal to 4. And now if you solve this, you get x squared minus 4 equals 0, and you can factor it. Well, this is one way you could have done it. And now you get two solutions. You get x equals 2, and you get x equals negative 2. And so you actually have an extra solution. The original one was just x equals 2, but we picked up this other solution. So when you're squaring problems and squaring equations, there is a possibility that you might pick up an extra solution, and that's called an extraneous solution. So it's very important that you check for those solutions. So let's go ahead and look at these next two examples. On the first one here, we want to isolate the square root, so we'll subtract 4. That leaves us with negative square root of x plus 6 is equal to x divided by negative 1. And you get negative x. So we've isolated it. Now we want to square both sides. And so we get x plus 6 is equal to x squared. It is a quadratic, so I'm going to subtract the x and subtract the 6 to get it equal to 0. And then we need to solve by one of our methods of solving quadratics, which on this one it looks like I can just factor it. So it'd be x minus 3x plus 2. And we get two possible solutions, x equals 3 and x equals negative 2. Now we want to plug them back in and check to make sure they are correct. And when you do that, you will find out that x equals 3 does not work and only x equals negative 2 does. So if you plug in 3, it'll be 4 minus the absolute value, 4 minus the square root of 3 plus 6 is equal to 3 plus 4. So that'll be 4 minus the square root of 9, which is 3. So 1 equals 7 does not work. And then if you check x equals negative 2, it will work. So x equals negative 2 as your only solution. So we did have an extraneous solution on that one. On example B, we got 6 times x plus 2 raised to the 2/3 is equal to 24. Well, this is still a radical. Rational exponents are radicals. So let's isolate that by dividing by 6. So we get x plus 2 is equal to 4. X plus 2, raised to the 2/3 is equal to 4. Now, how do you get rid of the 2/3? How do you undo that? Well, if you have an exponent and you want to undo, you can raise it to the reciprocal. So if you raise it to the 3/2, what's 2/3 times 3/2? It's a power to a power. So it just cancels and you're left with x plus 2 is equal to 4 raised to the 3/2. So you'll have to evaluate that. And 4 to the 3/2, remember, it's the square root of, the 2 represents the root, it's the square root of 4, and then cubed. So it'd be x plus 2 is equal to the square root of 4 is 2, 2 cubed is 8, and then you subtract the 2, and you get x equals 6. Once again, we want to plug this in to make sure it does work. So it's 6 times 6 plus 2 raised to the 2/3 is equal to 24. So that's 8 raised to the 2/3. Now the 2/3 is the cube root. So this is the cube root of 8 squared. So the cube root of 8 is 2. 2 squared is 4. And so we get 24 equals 24. So x equals 6 is the solution. We didn't have any extraneous solutions on that one. On the first example here, 4 minus the square root of x plus 6 is equal to x plus 4. I'm going to show you on the graphing calculator how you can solve this, or at least check it graphically, and at least be able to find an approximation. So the first thing that you want to do is you want to set it equal to 0. Remember when you solved quadratics, you set them equal to 0. I just did that a second ago, and you solved for that x value where it crossed the x-axis. Well, that's what we want to do with any type of equation. So we set it equal to 0, so I subtracted the x and I subtracted the 4, so the 4's canceled and it became negative x. And so I plugged that into the calculator. I graphed it, that's what it looks like on the second one, and then I went to calculate. So when you go to calculate, it's above the trace button, so press second trace, and you'll find number 2 says 0. That's what you want to find. Once you hit that, it's going to ask you left bound. So pick a value to the left, which I picked about right here, of the 0. Then it says right bound. So pick a value to the right of the 0. And then it's going to ask you to guess. So get close to the 0 itself. And then when you press enter one more time, it'll give you the 0 is at x equals negative 2 when y is 0, but we already know that. We set it up because y is equal to 0. So that's a way that you can actually check your answers graphically, not just with square roots, but with any types of functions. Alright, here's one more that has the repeat steps 1 and 2 if necessary, because there's 2 radicals here. So the first thing is we want to isolate the first one. So we'll add the other one to the other side. So that'd be 2x minus 12 plus 1. They are square roots, so let's square both sides. Now when we square the left side, the radical goes away. When we square the right side, it doesn't go away completely because you have a binomial times a binomial. So you're going to have to distribute that out. So take your first terms here, square root times the same square root gives you 2x minus 12. So it goes away right there. But then your middle term, you're going to have 1 square root of 2x minus 12. 2x minus 12, yeah. And then 1 times the square root of 2x minus 12. So how many do you have total? 2. So that's plus 2 times the square root of 2x minus 12. And then 1 times 1 is 1. So now you need to go through that step 1 and 2 again and isolate the second radical. So I've isolated the second radical all the way down to, there's a 2 in front. I would normally divide by 2, but it doesn't divide evenly, so I'm just going to leave it there. It doesn't matter because it is a product. So we're going to square both sides. We have a binomial squared on the left, so that's going to be x squared minus 24x plus 144. Is equal to 2 squared is 4, and then you square the square root and it goes away, so that's 2x minus 12. Now it is a quadratic, so we need to set equal to 0. So I set it equal to 0. I got x squared minus 32x plus 192 equals 0. Now this might be one that we don't necessarily know how to factor. It is factorable, but even if you don't know how to factor it, you can do the quadratic formula, complete it in the square, you can solve another way. But it does factor into x minus 8 and x minus 24. And then you get 2 solutions, 2 possible solutions. X equals 8 and x equals 24. And you have to plug those back in to check to see if they work. So for example, you got 8 plus 1 minus 2 times 8 minus 12 should equal 1. So the square root of 9 is 3. 16 minus 12 is 4. So the square root of 4 is 2. So 1 is equal to 1. So x equals 8 works. What about 24? Well, that's the square root of 24 plus 1 minus the square root of 2 times 24 minus 12 should equal 1. So that's the square root of 25. Square root of 25 is 5. You got 48 minus 12 is 36. The square root of 36 is 6. So it looks like we get negative 1 is equal to 1, which is not a true statement. So your only solution to this is x equals 8. Now the last ones we're going to solve are going to be radical inequalities. So we have the square root of 6x minus 5, but it's less than 4. If we're not solving for exact values, any value that would be less than 4. So we solve it the same way. We square both sides, we isolate it, and then get rid of the radical. So we're going to square both sides. So that'd leave us with 6x minus 5 is less than 16. And then you can solve. So you add the 5. You get 21 divided by 6. Be 21 6. That would reduce to 7 halves. Now, if that was it, that would be nice, but you also have to think about the domain. What's your domain for a square root? Well, there's a restriction. You can only take the square root of 0 or larger. So whatever's underneath the radical, in this case 6x minus 5, the domain must be greater than or equal to 0. All right, and that's true for all even indices. So now we solve this, and we get x is greater than or equal to 5, 6. So what's our solution? Well, two things have to occur. We want all values that are less than 7, but we want to make sure that all those values are also greater than or equal to 5, 6. So if you get a number line and you think about this, you have 7 halves and you have 5, 6. So here's 5, 6, here's 7 halves. You want values that are less than 7 halves. Those are the ones that solve it, but your domain only includes values that are greater than or equal to 5, 6. So what are your solutions for x? Anything in between those two, including the 5, 6, but not the 7 halves. So your solution is all values greater than or equal to 5, 6 and less than 7 halves. And write that in interval notation. Okay. On the next one, it is a cubic. That's okay. We're still going to isolate it, so we'll divide it by 4. So it's the cube root of 3 minus x greater than or equal to. Now if you divide by negative, you do have to switch the inequality, but that's not what happens here. Now we cube both sides, and we get 3 minus x is greater than or equal to negative 8. Subtract the 3. Divide by negative 1. We do need to switch the sign because we did divide by negative 1. So x is less than or equal to 11. Now on this one, what is the domain? Well, the domain is all real numbers. You can plug in whatever you want. You can take the cube root of any number, positive, negative, 0. So we don't have any other restrictions on this one. So if you do think of it as a number line, you have all these values that are less than or equal to 11, and then your domain covers the entire number line. So where do they intersect? What do they share in common? All of these values. So your solutions to this are all values that are less than or equal to 11. All right, so pay attention to what that index is as to whether you need to check the domain or not. Okay, and in class I might show you another way that you could possibly look at this as well.